Thank you for coming to this seminar. I know Professor Garimella starting from when I was a student at Georgia Tech, and I've been following his work, and it's very good to have him here. We're excited about what he's going to talk about his work. And Professor Garimella is the Hightower Chair in Engineering and Director of Sustainable Thermal Systems Laboratory at Georgia Tech. He had held prior positions as a research scientist at Bethel Memorial Institute, Senior Engineer at GM, Associate Professor at Western Michigan University and Iowa State University. He's a fellow of the SME, past associate editor of the SME Journal of Heat Transfer and Journal of Energy Resource Technology, and editor of the International Journal of Air Conditioning and Refrigeration. He also held other editorial positions that are too many to list here. He has mentored over 75 postdoctoral researchers, research engineers, and PhD students. That's a long list of students. He has published over 350 journals, a textbook on heat transfer and fluid flow, and a book on condensation. He has been awarded 17 patents. He the recipient of NSF Career in 1999, Austrian Investigator Award 1998, and SA Educational Award for Engineering Educators 1998. He received the SMA Award for Outstanding Research Contribution in the field of two-phase flow and condensation. He was a faculty fellow at the Iowa State University and Woodruff School of Georgia Tech. And along with that, something that doesn't show up on his resume, I know when I was a student that he's a very good teacher as well. And so we look forward for his talk, and the floor is yours now. We're glad to have you here.
Thank you, Solomon. Let me start by saying that the reason Solomon is doing so well is because he had the fortune of not having taken a single class from me. So I didn't have a chance to spoil him. One thing that may not be immediately obvious about me is that I received my master's and PhD degrees from a school called The Ohio State University. It's actually against my religion to come here, but Solomon actually suggested that I come here, and I couldn't say no to a fellow Georgia Tech person. And so I'm here at the place up north. I can't say the other word, okay? Anyway, I'm here to share some thoughts about practical pathways to energy decarbonization. Everyone is talking about energy decarbonization these days, and we can turn the lights down a little bit. And I want to give you my take on what decarbonization means and how we should approach it. We're going to focus on practical pathways, not just some esoteric ideas that end up in papers in Nature and Science and never show up in Walmart or Sam's Club or whatever else you go to. So I will start by giving you my idea of what decarbonization is about. Now the slides aren't moving. It should move.
Did the computer freeze, or if you go page?
Excuse me, guys, we have some technical difficulties. I'm sorry about this. I'm not sure why.
Stop.
participant can now see your application. He's doing that on the slide. Oh, okay, it works.
Thank you.
Okay. So if you look at the electricity, both the consumption and the generation, this is the required electricity today. And this much is being generated by fossil fuels, and this much is being generated by renewable energy. So obviously we are dependent on fossil fuels right now. But if we want to do this decarbonization, and we want to do that through electrification, which is the approach being advocated, then all these needs that are being satisfied by fossil fuels, by thermal energy, and so on, are supposed to be done using electricity. Well, that means your electricity demand will go up. And there are some target dates that people have mentioned that we want to be decarbonizing by year 2030 or 2050, and so on. So, well, how does that fit in with our ability to supply that electricity? Well, we will see an increasing contribution of renewable energy because people are making a lot of progress on it. But even at the most optimistic rates, this is the kind of electricity production that is possible with renewable energy. Whereas our needs are here, and this is the part that can be done through fossil fuels and so on. And this is where my definition of what carbon-free electricity is. I also include nuclear energy and so on. So clearly, there's a problem. There's a shortfall. We need more energy. We need more electricity. And we have nice goals of wanting it to be carbon-free and so on. But we have to figure out what to do about this part. So are we looking at the control volume properly? It's nice to say, well, I'm going to be carbon-free, and I'm going to generate it all through solar, wind, and all those kinds of things. And then you'll have this shortfall. And then the real way to look at this is to look at all the available options. It's not available goals, but what is the reality? So the control volume definition becomes kind of important. So then, do we really need to supply everything using electricity? After all, a lot of our end users are thermal. When you take a shower, you're not taking an electric shower, you're taking a hot shower. So if there is thermal energy possible, why not use some of that? It's heat the solar back. We can use solar thermal collectors for water heating, for example. We can use biomass or waste heat driven cooling systems, which I'll talk about later in the day. So maybe we can use all the tools that are available for us and still have that same goal of going carbon neutral. So if this is the same slide, if we want to keep this sort of unrealistic goal of producing all our needs through this electrification mechanism that people are talking about, then we have this shortfall. But if we use the tools available for us, that is, when you have the end use of heat, try to use that heat, then our electricity demand will go down. You may have heard, even as recently as a few months ago, there are many brownouts and blackouts in electricity in places like California. They don't have the ability to supply the electricity. Texas suffered mightily last year when they had when it is possible, and then to use electricity otherwise. So if you look at carbon emissions that stem from that, if you want to do it through this approach of total electrification, you're not going to be reducing the carbon load, whereas you can indeed do that by using all the tools available to you. So with that background, I'm going to talk about some of the research we have been doing and some of the solutions that we have been trying to come up with to address these comprehensive challenges. So what are some of the challenges facing us? Well, first of all, we need to understand, as thermal engineers, we need to understand hydrodynamics, heat and mass transfer. I will spend very little time on that today. And then I'll talk about things that need to be miniaturized, approaches of integrating things into systems, and fabrication aspects, because an idea is only good if you can implement that in manageable packages and if you can build that. I'll talk a little bit about carbon capture. I'll also talk about the simultaneous problem that's facing us, which is water use reduction and purification. I mean, there's a real shortage of water, so how do we address that? Other needs, such as you and I, if we have to wear clean clothes, we have to dry our clothes, and that's a very, very energy-intensive process. Can we do something about improving that? Thermal storage, with all the renewable energy, their storage is very, very important. Short-term storage is possible, but when you start storing thermal energy over the long term, then there are heat losses. And can we do seasonal storage by coming up with some clever ways of doing it? And then can we also do something to help with the load itself, these buildings? Can we do something to manage the demands so that our needs are lower so that we can meet it better? And we all have to eat, and I'll have something to say about the aspect of food availability too. That's kind of the outline of the talk. So one versatile that's okay. If you look at heat pumping, what is a heat pump? It makes heat or species move in directions where they don't want to. Heat wants to move from hot to cold. But when you are air conditioning a room, you try to make the heat from a colder space and turn it into the outside. In the winter also it's the same. So sorption makes it possible to make low-grade energy move up. Let me see if I can get this. We don't use Zoom at Georgia Tech, so I'm a little. No, the title is. You just have to move it now. Yeah, please.
It's also distracting for the audience to be able. I'll just move it here so that the Georgia Tech label is gone.
Okay, I think that's better. So a lot of our research has to do with sorption. And what does sorption do? It makes the heat or species move in directions where they don't want to do. And we are trying to make low-grade heat move uphill. This is ridiculous. You have to click on this one. Okay. Yeah, I'm sorry, guys. I don't know what's going on here. Anyway, in sorption, what you're trying to do is to move. You're trying to swing the temperature and the pressure. So you have three parameters now. Instead of just pressure and temperature, you have a concentration, you have a species. So this is a thermal compressor. And I'll talk about a variety of ways in which you can use this idea for all the needs that I mentioned earlier. So what is a thermally driven heat pump? Well, it's a combination of an engine and a heat pump, okay? So you take the efficiency of the engine, the Carnot function for it, and then the COP of that, and you multiply them together, so you get the thermal quantity. Thermally activated heat pumps, in sort of more familiar terms, is this is your air conditioner. This is the air conditioner that is in every building. It takes some electricity and it pressures the refrigerant to high pressures, condenses, expands, becomes cold, picks up the heat from the house, and then sends it out. But the problem with this is it uses synthetic diffusers that are being phased out, and it uses electricity, which again, as we saw, it's hard to produce through renewable energy just yet. So one approach is to take heat, and this could be solar energy, this could be biomass, this could be waste heat. You use that to boil off a refrigerant at high pressure, and then this part of the cycle stays the same. It's a condenser, expander, evaporator, and then you absorb it back into the absorber, into the liquid. So now you're pumping a liquid instead of compressing a vapor, which requires much less electricity. Now, you've seen that you've replaced one compressor with a bunch of heat exchangers and a pump. So it's been a little difficult to introduce this to the general public because it makes the components larger, perhaps more expensive. So this is where our understanding of heat and mass transfer at the micro scale comes into play. And we have come up with technologies that will miniaturize these so that they become palatable to the residential customers and so on. People have taken over the years many different approaches to make the performance of heat pumps better. This is a simple heat pump, the simplest of the cycles. But then they've come up with sort of internal recuperation. This is called a double effect cycle. These are two absorption cycles that are coupled to each other, one at a high temperature, the other at a lower temperature, to get a lot more internal recuperation. And then within the cycle itself, they've tried to recuperate from the hot portion of one component to the cold portion of another component and so on. But we think that this approach, at least in the beginning, is difficult because you're trying to introduce a very complex and very expensive system for a small gain in COP. So we took the opposite approach, saying we'll stay with the simplest cycle, but we'll try to make it smaller and much less complex. And so we have to match these types of systems to the kind of heat that is available. So we came up with this sort of temperature selection chart. These are various types of waste heat that are available at different temperatures. And so if you have a data center waste heat, well, it's very cold heat actually. And so you can use a heat transformer to actually upgrade the heat to higher temperatures. If you have a microturbine exhaust, which comes up at high temperatures, then you can design absorption cooling systems. And so we came up with different COPs and so on. This is waste heat that you were going to throw away, and we're utilizing it for some of the common end users. So, I mean, we did system level analyses, we did develop components for it and so on. And then we wanted to actually build them. So we want to understand the heat and mass transfer. And when I saw some of the experiments going on today in Solomon's lab and so on, they are trying to understand droplet behavior. We did this, this work is quite old. The idea here is when you're building heat exchanger, this is perhaps a condenser or an absorber or something. Liquid has to fall down and absorb vapor as it is falling down, and the heat of absorption has to go into the liquid, into the coolant that's going inside. Previously, people were modeling all of this as uniform liquid films, which magically show up on the next tube without worrying about all this inter-tube droplet formation, the wave formation, and so on. So we took a closer look at it. We said, okay, the drop actually extends to a small, forms a sphere, extends, then breaks up into small droplets. When it falls on this, it splashes. There's a new boundary layer for temperature and for concentration that is set up. And then when the drop falls here, on the next tube, there are these wave patterns that are set up, that are spreading in this way. And then some droplets, they don't behave. They never want to join the mass. So all these phenomena affect the heat and mass transfer. So then we did some very detailed analysis of the interfaces, calculated the surface area to volume ratio and so on. You want a lot of surface area for the volume of liquid you have so that more absorption can take place. So we quantified that, and sure enough, we found that once the droplet breakdown starts happening, you get a lot of surface area to volume ratio, and therefore you can get better absorption. So with that background, we developed for our same experimental conditions from first principles computational models of a fully 3D resolved, temporally resolved analysis. And you can see that it is replicating all those features, the droplet formation, the droplet elongation, and then you'll see it'll break up, and you'll also see these saddle-shaped waves that are coming. So now we have a good understanding of how to design these components. And we've done similar work on evaporators. These are rectangular tubes which are being used more and more in industry. You don't want this film to be so thick and create additional resistances. So we have come up with designs that avoid those. Sometimes it's also difficult to distribute the flow properly. And so we've come up with nice distribution devices so that the entire surface is being utilized. And then we've done some heat and mass transfer, coupled heat and mass transfer analysis. And you can see that the liquid is picking up new species, and that heat of absorption is being deposited into that liquid. And so it starts heating up as it leaves the cooled tube. And then once it falls here, then it is being cooled again by the tube. So this sort of periodic motion and the heat and mass transfer we've analyzed so that we can use them for design tools. And then it gives us guidance that, hey, if you have a bunch of fluid that you want to flow over tubes, don't do this because this is too thick a film of liquid and it is presenting a lot of resistance to the heat and mass transfer. So this gives us design guidelines too. So with that knowledge, many years ago, we built a set of components that are very thin microchannel tubes that are arranged in this crisscross pattern, and liquid flows from the top to the bottom, and vapor flows from the bottom to the top and absorbs, and that heat of absorption is sent into the microchannel tubes, which have high heat transfer coefficients. And then on the surface also, with all this splashing and mixing, the heat and mass transfer improves. So this is a very small component, about 5 inches by 5 inches by approximately 13 inches or so, 13, 14 inches. So this is one component for a residential absorption system, residential cooling system. You put 4 of them together and you have the entire heat pump. The beauty of this is this can function as an evaporator, as a condenser, as a controller, and a remote tube. The same geometry, okay, with some small modifications in the trays that feed the liquid. A few years ago, we came up with this idea and we applied to ARPA-E and got some funding for that. The basic idea was, I told my PhD student, look, we've done quite a bit of microchannel heat exchangers, we've developed heat pumps and so on. Let's try to build an entire heat pump, not just one heat exchanger, that is the size of the textbook we use for heat transfer. These drawings are to scale, and the product of his PhD was this heat pump, which is indeed smaller than the heat transfer textbook. The way we made that is we take very thin sheets of steel, 0.5 millimeters, and then we etch 0.25 millimeters deep channels into it. And then we stack a bunch of them together and we put a cover plate on it. And this is a heat pump. So how does it function? The internal passages are arranged in such a way. The etching is done in such a way that this is the heat generation where you provide the heat for the vapor. You purify the vapor, you condense the vapor, some internal recuperative heat exchange, evaporation, absorption, and again, some recuperative heat exchange of the solution. So all these components are in one plane. And so we take one plate like this and another to close it, and that's a heat pump. That's a full heat pump, but it only transfers a few watts of heat. And so it stacks many of them together, so there is a modular, versatile design. That device actually transferred 300 watts of cooling using 800 watts of waste heat. Over the years, we have improved the design. We actually manufactured it and so on, and I've shown some examples of scale-up components. So one of the tricks in this business is not just you want to increase the heat transfer in one single channel or in one component, but you want to build them in such a way that you're integrating multiple components into the same envelope so that you don't have so much plumbing going in and out of it, a lot of dynamic losses, pressure drop losses, and so on and so forth. So this here combines 3 different components into one vapor generation unit with different etching patterns. Okay? So you feed in the solution here, there's some adiabatic heat and mass transfer that happens here, adiabatic mass transfer that happens here. Then you fill up these pools, and then there's a combination of pool and film boiling that happens to generate the vapor. And as the vapor is rising, it exchanges some mass that becomes purer. And then you send cold fluid on the other side to purify that further. It's a reflux condenser that gives you pure ammonia at the top. So multiple components integrated into one package. And this is the other side where hot and cold fluid can be sent to make those processes happen. To further extend this, we have come up with these small distillation columns. They're only about that big. Okay? And so here again, we are providing a nice serpentine path for the liquid. And then there are passageways for the vapor to rise up, and there's intense heat and mass transfer between the 2 phases. And then we've actually done flow visualization studies to understand how this vapor liquid exchange happens, which has then guided us to build these kinds of components. And with these, we trace the interfaces like we saw in your lab. And we have a good idea of what the interfacial heat and mass transfer area is so that we can design these components. So this is, we detect the interface, and then we can use heat and mass transfer models for it. One other thing we did last year is we introduced some surfactant into the fluid so that we can provide better interfaces. You can see that it's the same flow conditions, but if you throw in a little bit of surfactant, you get much better agitation of the interfaces. So the heat and mass transfer between the phases and within the phases improves. And you can get, without surfactant, this was the thermal resistance. With just 500 ppm of 1 octanol, there's a 37% in the resistance involved. Now, those processes were using etching, photochemical etching, which is a slow and expensive process, as many of you know. So we wanted to see if this can be mass produced so that it becomes attractive to the customer. Well, we came up with a stamping process instead of that. And stamping is a centuries-old process, but stamping hadn't been done at these kinds of resolutions. And so we came up with designs that would make that happen. So high volume stamping is possible. And so this is a stamp microphone that is replicating what our original design was. And then we brazed it instead of diffusion bonding, which is again very expensive. We brazed it. And in Michigan, you will be very familiar with the brazing process because all the car condensers, radiators, and so on are mass produced using brazing processes. So we've helped with the fabrication of these kinds of systems. And then we built overall systems with a one-time system, one-time cooling, refrigerant cooling. The components look like that. This is something that we did for the US Navy, where they have in their forward operating bases in tricky places. It's very expensive to transport fuel there, diesel fuel there. If you send it, it's more than 20 times more expensive than here. And people are getting killed trying to carry that fluid over there. And so we want to use all of the energy that this fuel can give you. So that fuel is used in diesel generators to first produce the electricity, and the waste heat is used in this absorption heat pump to provide cooling to the soldiers in their tents and so on for free. Okay. And this is, to my knowledge, this is the only system that's available that at 52 Celsius ambient, okay, 52 Celsius ambient, it is providing cooling to these tents without using any electricity. This is another PhD student's project where we all have water heaters in our homes, for the students, perhaps in your folks' homes. And there's a storage tank, and essentially it's a well, I said, how about we put a heat pump on top of this? So we've actually bought the storage tank of a heat pump of a water heater. And my student built this absorption heat pump that goes on top of this. With this, we were able to reduce the energy consumption. So for every BTU of heat that goes into the system, due to the heat pumping, the customer, the user, the person who's taking the shower gets 1.7 BTU. So we're reducing the gas consumption, the fuel consumption to provide the heating by almost 40 to 50%. So these are some of the innovations we have done. And then we took that idea and built a residential heat pump for air conditioning and heating that can handle temperatures as high as 44 degrees. Okay. And we'll be experiencing those kinds of temperatures. We need to be ready for that. This, of course, is a lab model where we actually built this. It runs and provides the cooling. More than a typical residential unit. Okay, well, even those things, as you saw on the initial slide, need a pump to circulate the solution. Well, what if you're transporting vaccines and medicines, which are particularly relevant in today's world, to remote areas that don't have electricity? And even if they do have electricity, what if the pump breaks down in that remote place? You're not going to FedEx a pump. It may take months, it may take years. So let's try to get rid of it and make a completely passive system. It's a fully thermally activated refrigeration cycle. And the way it works is, instead of a pump, the actual buoyancy of the vapor and the liquid pumps up that liquid. Okay. And so it's a circulating pump. And then there are different species in that fluid, in the vapor and liquid. The partial pressures are different in different parts of the system. And due to this difference in partial pressures, some portion of the cycle is cold, some of it is hot, as you want it in a heat pump. So with this, we were able to design a completely passive heat pump for those kinds of purposes. And to be able to do this, we did some high-speed photography, and then we dynamically digitized it, tried to find out what kind of vapor liquid holdup there was. And then we also did computational analyses to support that kind of work. Okay? Sometimes people think microchannels or microscale means very small things. Yes, they are very small things, but if you then apply them to very large systems, the benefits are even more. So this is for an aircraft carrier, naval ships and so on, where they have exhaust heat as much as 200 megawatts. So then we said, well, let's do a lithium bromide water absorption system to produce some cooling at sort of conventional 3-4 degrees Celsius. But then instead of using that, we will then couple it to a CO2 vapor compression system. And CO2 is a natural environmentally benign fluid. With that, we can get 51 megawatts of cooling at minus 40 Celsius. So in today's aircraft carriers and so on. There are sophisticated electronics that need to high heat for cooling. And then we have this pumped liquid at -40 that's available to do the pulse cooling whenever needed. So it provides this 200 megawatts of waste heat plus it provides 90 megawatts of cooling for the passenger cooling, and then -40 Celsius, 50 megawatts for those other transient loads, only with the 23 megawatts of input. So we use our knowledge of falling films that I showed you, the falling film evaporators, and this is phase change of water, which is an excellent heat transfer process. It can give you 30,000-40,000 watts per meter squared Kelvin heat transfer coefficient. And then CO2 flowing through this. Again, CO2 is an excellent working fluid. And when it is condensing, that heat transfer coefficient is extremely high too. So we were able to transport 40 megawatts in a very small package across a delta T of only about 2 or 3 degrees. I was talking to some of your colleagues earlier today about carbon capture. One of the techniques we have come up with, along with our chemical engineering colleagues, is adsorption. Not absorption, but adsorption, where you take these hollow fibers with a polymer matrix with adsorbent crystals in there, and then you take the exhaust from the power plant, and then you take it in here, the exhaust comes here, CO2 gets adsorbed in these particles, and the heat of adsorption is taken away by liquid flowing through that. So that's one phase where that adsorption is happening. And then after that adsorbent gets saturated, you send hot fluid through so that you can pull out the CO2 that you absorb and sequester it. Okay? So we developed this process, but CO2 capture is successful only when it doesn't need additional energy to run it, large amounts of energy, because where is that energy coming from? It may not be coming from renewable energy, so we have to be careful with the energy budget. That's the part that we brought into the picture by saying that, well, as adsorption is happening, this flue gas is flowing from one side of the heat exchanger to the other. And there's a temperature front, there's a temperature wave that is going at you. Why don't we change that and do recuperative heat exchange? As heat is deposited or as cold is deposited, we pick all that up at small delta T, and then when it's going backwards, we'll pick all that up too. So then the additional heat that is required after all this recuperation is done is a very, very small amount. With that, we were able to get very good product purity at very small energy consumption. And then we put it to a power plant. We actually did an entire power plant analysis, including the carbon capture and a realistic power plant cycle with the adsorption and desorption incorporated into it. So the flue gas flows from the boiler into the carbon capture tubes, and then CO2 is separated, and then CO2 is compressed to the required pressure. And then we compared it with the other technologies that are being proposed, and our study beats all of them. Okay, next topic is clean water. Well, we all need clean water. And the statistics, both in the US and worldwide, are scary. People are dying because of lack of access to water. So what do we do about it? One of the things that one of my students did is we have expertise in absorption heat pumps for heating and cooling of buildings. That's what we built for many years. And he suggested, well, why don't we go through that heating and cooling process, but also as a side benefit, get water purification. So now this is an open cycle, not a closed cycle, where this refrigerant that is going through, which could be water, it could be ammonia, but in this case it's water. You draw the dirty water, the clean water from your showers and so on, and then you put it into an evaporator, it gets evaporated, so pure vapor is being liberated, and then you send it through the absorber, and it goes up here, goes through yet another distillation process, So double distillation while refrigeration is happening or heating of a house is happening in the winter time. And then here you get pure water. You take in dirty water and you get pure water. So this was the cycle that we conceptualized. And then we can choose based on the residents' needs. You want heating right now or you want water purification? That energy that you have can be distributed. And then we did a study of different working fluids to combine different absorbents to combine with the water and found the best ones. So we evaluated it based on COP and also the product ratio. And we built this system. So this is the chamber that we have that operates at 3 degrees Celsius. So it's a very low pressure system. And he built this system. He demonstrated using synthetic gray water that we can get pure water out of it. Another application or another place where the water needs are becoming a crisis is power plants. As you know, power plants have cooling towers, and the cooling towers consume an immense amount of water to generate their electricity, and it becomes harder and harder to support that as water supply goes down. In fact, 38% of the US freshwater use is for power plant cooling. Okay? And the freshwater costs increase. So instead of cooling towers, can we do dry cooling of power plants without using any water at all? Well, if we can, of course, do that, but it will need humongous heat exchangers to make that happen. Or the power plant efficiency will go down, and nobody wants the power plant efficiency to go down because then you have to burn more fuel. So it's a catch-22. So we decided to focus on improving the heat transfer in these power plant condensers so that we can make them perform much more efficiently and eliminate the need, or at least reduce the need for cooling towers. These are some representative air-cooled power plants. There's one in South Africa. This is one of those. There's actually one demonstration unit in California also. We wanted to reduce the size of this so that we can get rid of cooling towers but not end up with this massive capital investment. So heat exchanger consists of two sides, the air side and the condensation side. So we came up along with the help of colleagues ways to improve both sides. So if these are heat exchanger fins, we put thin mylar sheets that due to the air that is blowing over them, they will oscillate and they will create mixing in the fluid and they will enhance the heat transfer. For the condensation side, this is what it would be without any enhancement. And then we acoustically enhance it by essentially putting a helmet resonator. And this creates a lot of agitation in the flow, which increases the heat transfer coefficient. So this is that technology. You see, these are the fins of the heat exchanger, and these are the reeds that are inserted, mylar reeds that are inserted, which cause that oscillation. And then we measured we got heat transfer enhancement of up to 60%, depending on what conditions we are using. Of course, there's a pressure drop penalty too, but the pressure drop in the system is very large anyway compared to the pressure drop in that simple heat exchanger core, whereas you're getting so much heat transfer enhancement. So we can take this. On the process side, again, through this. So those of you who know something about condensers, it starts out as a vapor, very high velocity, very high heat transfer coefficients, no problem at the inlet. As it goes towards the end, it slows down because it is now liquid instead of vapor. There's not that much shear, and it presents a huge thermal resistance to heat transfer. You can see that there's a lot of dead heat transfer fluid that is not doing anything. By doing that acoustic enhancement, we have shown that we can get 30% heat transfer enhancement at the places that it really needs it. This part doesn't really need all that heat transfer enhancement. But often that last portion of the condenser becomes the governing one. And so we've been able to get rid of that dominant resistance. So I talked about clothes drying. You may or may not be familiar with this, but this will ring true. How do you dry your clothes? Well, they're wet. They come from the washer and they're cold. For us, they're heated up to the saturation temperature. And then some sort of heating takes place, and then it rises to even more higher temperatures, and then some more heating takes place. So when it comes out of the dryer, the clothes are hot, right? And they're hot and dry, and then there's a cooling cycle. So you can see that there are possibilities for heat recuperation. There's a hot portion of the cycle, there's a cold portion of the cycle. Is there a way we can use this phase to preheat? Well, it's not like you'll take the exhaust from the dryer and put it back into the inlet of the dryer, because you spend all this energy to remove the moisture from the clothes and put it in the airstream. You're not going to bring that same moisture back. It is hot, but it's also moist, so that defeats the purpose. So first of all, we modeled the textiles from the fiber to the cloth to the entire garment pieces on this sort of rotating drum, accounting for the rotation of the clothes. And then we were able to predict, these are measurements and predictions of what is actually happening in the dryer. And this is PhD level research. You go and wash your clothes and dry them. We have a washer and we have a dryer. And there is something known as a standard load, standard laundry load. If you go to the industry, you get a bunch of towels, literally a bunch of towels of a standard weight, and you're only allowed to run those experiments for X number of washing and drying cycles, because the lint keeps going away and the nature of the clothes changes. So this is my PhD student's research. He's now in Evelyn's lab as a postdoc. Okay? So we came up with different ideas. Well, you can recirculate the fluid, but through a recuperator. So you just simply remove the heat and feed it back. If you remove the moisture and you feed it back. So first of all, we did some optimization of the RPM. Then we did recuperative heat exchange. And then we did thermal energy storage. So we took desiccant, those silica gel beads that you get with every electronics component. We had a tank of that. We sent it through this. It took away all the moisture and produced dry, hot air, which then we used. With this, you can see that the drying time was reduced substantially by almost 23%. And then the energy, this SMER is simply a measure of kilowatt hours that are used per kilogram. And that also was reduced by 23%. There are other people looking into reducing the energy consumption, but that also takes a long time. You don't want 2 hours to dry your clothes. So this thing does both time reduction as well as energy consumption reduction. I have 2 more topics to talk about and we'll close it out. As I mentioned before, thermal storage, everyone is talking about thermal storage, but thermal storage has one big limitation. The longer you want that heat to stay, the more the heat losses. So the round trip efficiency of that storage keeps decreasing as time goes on. So instead of storing it as heat, we store it as separated chemical species and then combine them when we want them. So that's the system. Through our absorption expertise, we came up with this technology, but it's a simpler cycle because it doesn't need an evaporator. It doesn't need to be related to what the ambient temperature is. You can do it on a very cold day, on a very hot day, and so on. Basically, you separate the species and you store them as concentrated solution, solid solution, and water storage, and then you mix them on demand. And there's a few other nuances. We do some recuperative heat exchange and so on. And then we said let's combine that with phase change material also. And we are able to demonstrate that you can store using this kind of technology heat either for immediate use using phase change materials or for long-term use using this absorption technology. There is demand side management. So this is an actual neighborhood. There are two neighborhoods, one in Alabama, Birmingham, Alabama, one in Atlanta, near Georgia, where these houses are instrumented. They're all similar appliances, similar houses, and so on. The idea was to say, well, maximize the amount of energy available for load shifting. So if one house is using some, so both on an individual house basis and on a community basis, and we trade between houses. And we also, this student is finishing up her PhD. There's solar panels on the roofs, there is batteries, electric batteries, and then there are water heaters. So why not heat the water when the utility rates are the lowest? And then when the utility rates are highest, you couple this to the signal from the utility, the instantaneous 15 seconds by 15 seconds rates. And then you decide, do you want to use the PV for it? Because the grid electricity may be too expensive. Do you want the stored battery? Or do you want to use the stored hot water? So it is not that easy. Conceptually, it is fine. But you and I, when our house meter reading is taken on a monthly basis, there's just one signal, right? The entire house energy consumption is represented by one signal, and you'll see some peaks and so on. So we are using some machine learning techniques to disaggregate this. So we know the signal of each component, and then we have this combination, and we try to see whether we can identify what that composite load was through this machine learning type of technique. So load disaggregation, energy forecasting, and then combine that to get demand side management. This shows that we can reduce the cost to the customer for building energy needs without reducing occupant comfort. Final topic, food. We all need. And in countries like India, for example, there isn't actually a shortage of food. The shortage of food. There's plenty of food produced. Farmers are very good at producing all kinds of vegetables, fruits, and so on. The only problem is, it's a hot climate. The food doesn't last very long. If you take it in a truck from one place to another, within a few hours you have to sell it to the customer, otherwise it's lost. It spoils. So is there a way to store that and provide the cold chain in a country like that, where electricity supply is not a guarantee? And so we said, there is biomass available. There are twigs and cow dung and stuff like that available. Why don't we use that as a heat source and build an absorption heat pump? So the way this works is that there is the activated carbon, and then there is ammonia, and then you use this biomass produced heat. You gasify it, and you produce the heat as a source. We're working with a company called Belief in India, and we have funding from the US IFT, the US India Technology Transfer Foundation. And so this is how it works. There's the biomass produces water at this temperature, and then we have the absorption beds, condenser, evaporator, and so on. It switch functions, and it's a batch mode process. Once the absorption happens, then you switch the bed into a dissolver and so on. And we have been building these. We have been helping this company build these, and also optimize the components by taking particle level heat and mass transfer to the overall adsorbent bed, to optimizing sizes of components, and trying to figure out how COP depends on all of these. And with that, we think we can efficiently use the agricultural waste. We can then provide the farmer a means of living. And then there's zero carbon footprint here. And all this food spoilage issue is taken away. And in India, you may have heard there are a lot of fog problems in the winter and so on. That will go away too. These are some of my current students who are helping me come and talk to you guys. I hope, despite the technical difficulties, something of this. Thank you very much.
you for the excellent talk, Professor Garimella. And anybody has any question online? If you have any question, you can write on the chat, or you can unmute yourself and ask. Yes, Jose.
You mentioned making a stamp and then the cost of the thermal etching. It requires significant production to develop those complex stamps, the dyes with stamps.
There is, of course, the initial cost that is available. So, but the point is, you would use stamping when you when you need mass production. You wouldn't be using stamping if you weren't supplying a product that you paid. But it's something like an air conditioning system, it's ubiquitous. Every apartment is 60,000. So the initial cost of that die is easily amortized by the number of units that you would be selling.
And I want to ask about the acoustically enhanced condensation. You said you saw 30% improvement. What's the mechanism? Is it breaking the boundary layer for the enhancement? And importantly, I want to know how the acoustic resonator, is it attached inside the tube or outside the tube?
Okay, so there are those two questions. The first question is, how does it actually work?
Yes.
So this works for fluid flows where there are interfaces. So the Helmholtz resonator creates these pulses in the interface, which first makes the interface become more wavy. And when it becomes more wavy, the shear pulls off, the vapor shear pulls off that crown of liquid that forms and breaks it up into smaller pieces. So there's more heat transfer possible. So the flow becomes far more agitated and more mixing mechanisms are there, which is what causes the heat transfer enhancement. You have to tune the frequency, you have to tune the amplitude based on the mass flux that you are interested in. But that's the principle. Where is this resonator? Currently, we have put it at the inlet, and then we point it towards the downstream flow. So it's at the header. So any heat exchanger will have a header. The idea is to put these resonators at the header so that you can target it to the location that you need it.
Okay, thank you. Any other questions? Online, actually, there is a question. Thank you for the wonderful presentation. I agree. What do you anticipate are the most significant issues associated with scaling to different communities, both the engineering challenges and the potential cultural challenges and opportunities? I'm particularly interested in the agricultural application, please.
Well,
This is Margaret.
I could guess that it is her. I mean, the answer to that could be 3 or 4 days long, but I'll try to capture some of the important aspects, especially the agricultural one is actually a very interesting situation. It is already a success story. I hate to call our research success stories, but it is because this company in India is actually selling them to the farmers. So that's already happening. Our contribution is that we are improving it, we are helping them mass produce and so on. The reason it is a success is as follows. Culture change is not needed for this. They are farmers, we are only asking them to continue to be farmers. And we are providing them an easier to use refrigeration system that they can use either individually or as communities. They have sold this to people who are individual farmers who are producing bell peppers or tomatoes or mangoes or anything like that, as well as milk producers. Milk is an essential staple in those countries, and so that has been very successful. The other thing is the governments can be double-edged swords, but in this case, the government has been pretty proactive in this, in providing loans to the farmers. That, of course, these are subsistence level farmers, and so without the loans, it would not be possible. So they are facilitating this. Finally, just like here, there are very large supermarkets in India too, companies called Big Basket and so on. So they are tying up with those. So right now there's a huge order for Big Basket for this technology, and we are selling that. And they are putting everything in the cloud. Not that the farmer will be interested in the cloud, but the investors, people like me, people like my students can actually see the temperature in the storage room anytime we want, so that we can tweak it from a distance. So I don't know, Margaret, if I answered your question, but the central point is you don't want them to change their lifestyles too much.
Excellent. This is awesome. Thank you very much. This is, I love everything that you said about that and the engineering systems as well. Super work, and thank you.
Thank you, Margaret. Thank you for the question. I have one more question from Rohini. I'm going to read it for everybody to hear as well. Really good talk, Professor Garimella. I agree. I have a couple of questions. One, very intrigued by the stamping process. Do you lose resolution tolerance compared to lithography? How limiting is this effect? And the second question is, why is the performance of phase change plus sorption based TES batteries TES better than having just one of the two? Are they storing heat at different temperatures and therefore better for flexibility?
Okay, so regarding the first question, it is similar to the question that asked. Yes, the tolerances possible with stamping are a little bit worse than the tolerances through etching and processing like that. However, this kind of design has so many degrees of freedom that we can actually change the channel dimensions, both the depth as well as the width of the channel, and then adjust the number of channels that we use in a plate and the number of plates that we use for that component. So while there is some loss in resolution and maybe even some loss in heat transfer coefficient, we can overcome that by adding maybe one plate or something like that, but then making the fabrication process many times cheaper and faster. As to the second question, the phase change is a thermal storage process. It has the limitations of heat loss and so on. The absorption process, the species separation, it is not limited by heat transfer, so it can last longer. But its efficiency is lower than that of the PCM. So if you want short-term storage, you use PCM. If you want long-term storage, you use absorption. And I think that's the flexibility that you were talking about. Rohini, is that answer your question?
Great. Yeah, thanks so much. That was great. And thanks for a great talk.
Thank you, Rohini. Any other question from the audience here? Or from online? Good. I think we're actually over time because the conversation was engaging. Let's thank the speaker.